Today, we're talking about DFA and DFM in PCB designs, and we're definitely talking about some common DFA and DFM issues or mistakes that can affect your prototype, and of course, some guidelines and solutions to prevent them. Design for manufacturing, that is DFM, is a process of optimizing a PCB layout to ensure it can be fabricated efficiently as per the manufacturer's capabilities. It focuses on material selection, stack up layers, trace widths and spacing, drill sizes and tolerances. Whereas design for assembly, DFA, is the process of designing a board to ensure the components are mounted and soldered efficiently during the assembly phase. DFA usually focuses on component footprints, polarity marking, pin 1 marking, part to part clearances, and component to board edge clearance. By following some DFM rules, you can ensure manufacturability and reduce overall board costs. It also helps you optimize design to prevent common manufacturing defect. DFM guidelines are crafted to align your design with your fabricator's capabilities. This alignment not only minimizes fabrication issues but also reduces design revisions. And finally, DFM helps you increase the yield, which is critical for high volume manufacturing. Let's discuss a few DFM guidelines for radio frequency boards now. Mismatched CT between copper and laminates often result in via pad dislocation from the contact pads. To minimize this risk, you can choose materials with a CT that is close to copper, around say 17 ppm per degree Celsius in the X and Y direction and under 70 ppm per degree Celsius in Z direction. Next is the thermal conductivity. So laminates with poor thermal conductivity can lead to overheating. So you need to opt for materials with a thermal conductivity above 0.5 watts per meter Kelvin at least. Also choose substrates with a glass transition temperature that is above 170 degrees Celsius because lower glass TG materials usually expand more under heat, increasing the risk of cracked vias, lifted pads or delaminated copper traces. Also, variations in dielectric thickness might impact your impedance. So always ensure uniform material thickness, ideally within say plus or minus 10% of the specified value. Building reliable stack-ups is a very critical step. You must tailor your stack-up based on at least these three parameters, that is the signal speed and operating frequency, the number of layers that is needed, and the current capacity and thermal requirements. Before finalizing the finished board thickness, make sure to check your CM's tolerances, typically plus or minus 10% of the target thickness. Also ensure symmetry in your circuit board stack-up because this prevents bow and twists. Usually PCBs show some degree of warping, and that is why we have a table here that outlines the criteria for maximum